So my favorite analogy of a class is a cookie cutter. And I'm just going to shrink this down like this so we have some more room. But think of the cookie cutter like this. There are built-in cookie cutters, so to speak, in Python where you can create an integer. You can create strings. And when you create a class, you are creating your own data type. So for our simple example here, since we are using the analogy of a cookie cutter, we're going to create a class and we're going to call it cookie. You're going to want Python to do particular things when you create a new cookie. And you do that with what is called a constructor. And it has a particular syntax. It looks like this. So it starts out looking like a function with the def on there. And then it's double underscore init, or some people say init, but to initialize this, and then another double underscore. And one of the things that is going to be different about a method than a function is the self keyword. If it has self in there, it is a method that is part of a class. And we'll talk a little bit more about that self keyword as we are going through this example. And then there is the parameter color in this case. And what we're going to do with that is color is what this variable is here. So if you pass this the color green, it gets passed to here, and self.color applies to the specific instance of color that we're creating. So we would create a new cookie like this. So we'll say cookie1 equals cookie, and then we'll pass it the color green. So cookie1 is the variable name, just like if you had a variable and you set it equal to an integer or a string. But instead of an integer or a string, we are setting it to be the type cookie. And we're passing it the color green. This gets passed to the constructor, and that creates a green cookie. So now it makes it a little easier to describe this self keyword. This particular instance of cookie, this one here, that is called cookie1 itself is green. And this will make even more sense when we create another cookie. So we'll create another one here. We're going to call this one cookie2, and we're going to say that this one is blue. So cookie2, different variable, it is a different cookie. We're going to pass this one to be able to create new cookies, but the color for the particular cookie that you're calling cookie. Okay, so we're going to go run this code, and then we have these print statements down here to check to see if the color has actually changed. So let's run this. And now we have cookie1 is now yellow, and cookie, we would call this class. Link classes for every one of our data. We would have a constructor write all the code for move something. So we're going to write all of that is how we're going to use classes. Okay, now let's talk about classes. So in this video, we're going to talk about pointers, and specifically, we're going to talk about how pointers work differently with different data types. And then we'll create a second variable called num2, and we'll set that to be equal to num1. So when we do this, we're creating an integer 11 somewhere in memory, and then we point the variable num1 at that integer. But the question is, what happens when we set num2 to be equal to num1? Are we creating a separate number 11 that num2 points to, or does num2 point to the same number 11 in memory that num1 is pointing to? So to test this out, let's flip over to VS Code. So there is our num1 equal to 11 and our num2 equal to num1 up here. And then we're going to print out the values of num1 and num2 here. But it's these two lines here after the. So now let's look at another data type that works in a different way than integers do. I'm going to create a dictionary. And to do that, I'm going to set dictionary 1 to be equal to dictionary 2. And of course, that's going to point that down here. And we'll have all three variables pointing at this same dictionary. For example, when we have a linked list, the nodes in a linked list are going to operate very much like a dictionary. So if you have two variables that point at the same node, you can change the these separated in our mind. So welcome to linked lists. This will be our first data structure. And to explain it, I'm going to start by bringing up a list. This is just the normal list that is built into Python. And then I'll go through and change this step by step to turn this into a linked list to highlight the differences between the two. So the first difference is that a linked list does not have indexes. So I'll remove the indexes here. The next thing is that a list is an contiguous place in memory. These are all right next to each other in memory. With a linked list, all of the nodes are going to be spread all over the place. Now, another thing that I like to do when I move to a different data structure is I like to change the color and the shape so we can keep these separated in our mind. So I'm going to change this from these being green squares, and I'm going to change them to purple circles. So also with a linked list, we have a variable called head, and it points to the first node in the list. Then we're also going to have tail point. Each node points to the next, to the next, and the last one is just going to point to none. So to emphasize that these are in different, I'm going to bring up a memory space, look more like this, and because indexes is how they compare to lists. So in this video, we're going to talk about linked lists, big O, and I'm going to walk through every method that we're going to create for a linked list and what the big O for that method is going to be. So I'm going to method is going to be to append a new node to the end of the list. So in order to do this, we have to have the last node point to it. Tail is going to point to it. And now we add it into the list. This is O of 1. The reason being, it doesn't matter how many nodes we have. Tail is going to point to it. Tail is going to point up a linked list. We have our head and our tail. And our first method is going to be to append a new node to the end of the list. So in order to do this, we have to have the last node point to it. Tail is going to point to it. And now we add it into the list. This is O of 1. The reason being, it doesn't matter how many nodes we have in the list. The number of operations to add it to the end is exactly the same. But what about when we remove the item like this? It would seem that all we have to do is have tail point to this node and we're done. But when we are removing from the end of a linked list, it's more complicated than that. In order to have tail point to that last node, we have to have that pointer there be set equal to something else that is pointing at that node. Remember, these are all just pointers, so we have to set it equal to another pointer. And the only thing that points to the 7 node is this pointer. So in order to get to that node, we have to start at the head, iterate through the list until we get to that pointer. Then we can set tail equal to that pointer, and that points it at the 7 node. But because we had to iterate through the entire list, this is O of n. Now let's look at adding and removing items from the other end of the list. This is O of n. Now let's look at adding and removing items from this pointer. So in order to get to that node, we have to start at the head, iterate through the list until we get to that pointer. Then we can set tail equal to that pointer, and that points it at the 7 node. But because we had to iterate through the entire list, this is the other end of the list. We need to have that 4 point to the 11 node. The head points to the 11, so we'll have the next pointer from 4 be set equal to head, and that points it at that node. And then we have head point at the new node, and that adds it into the list. It doesn't matter how many items we have in the list, it's going to be the same number of operations to add an item on the front of the list, so that is O of 1. Now let's look at removing that 4 node. The first thing we need to do is have head point at that 11 node. We can do that by saying head is equal to head dot next, and that moves that over. And then we remove that item from the linked list. Once again, this is going to be O of 1 because it doesn't matter how many items we have in the list, it's the same number of operations to remove that. Now let's look at adding an item somewhere in the middle of the list. Let's say we're going to insert that 4 after the 23 node. In order to find that node, we have to start at the head and iterate through the list until we get to that 23 node. Now we want the 4 to point at that 7 node. And this pointer here is pointing at the 7, so we'll set the pointer from the 4 equal to that. That points it there. We have that 23 node point to the new node, and that adds that into the linked list. But because we had to iterate through the list, this is O of n. Now let's look at removing that 4. The same thing happens here. We start at the head, and we iterate through the list until we get to the 4, like this. Let's move this down here. We want the 23 to point at that 7 node. So we're going to set the pointer from the 23 equal to the pointer that's going from the 4 to the 7, like that. Then we can remove the 4 from the linked list. Once again, we had to iterate through the list. This is O of n. So now let's look at lookup with a linked list. Let's say we're going to look for that number 23. And setting through until with a linked list, the index of 2, you have. This is something that is different than lists, because lists, you can do this by index as O of 1. But with a linked list, both looking it up by the value or looking it up by index is O of n. Okay, so let's move these out of the way. I'm going to bring in a table here that compares linked lists with lists. Now all the gray ones, it's the same either way, but there are a couple that are better for lists. Popping an item off the end and looking up by index. But with linked lists, if we add a remove from the beginning of the list, it's O of 1 versus O of n with a list. So I will attach this chart as a PDF to the resource. sources for this video, but that is the overview of linked lists. Okay, so now we're going to look at linked lists under the hood. So we're going to start with our diagram like this. And when we append an item, when we say this is equal to this and tail points to this going on, you have to understand first what the node is. So first of all, the node is all of this. It is not only the value, it is also the pointer. Both of these together make up the node. So still, what is it? It's essentially a dictionary where value is 4 and next is equal to none. So this isn't exactly how this works. You can't use the same syntax to access it, but you'll see it's very similar as we get to the end of this video. But you can think of it like this. So when you add this to the linked list, the 7 node also is a dictionary. But how do we have the 7 node point to the 4 node? We do it by just having the next value of that 7 node be the 4 node. And the same is true of the 23 node, and the 3 node, and the 11 node. And then we have head pointing to it, and then we have tail point to the last item. So this is basically what's happening when you see this. So let's flip it back to this. And look at this in VS Code. So up here we have a variable named head, and we just set it equal to this set of nested dictionaries. So I have a line down here of code that is going to print out the number 23 right here. So if you look at how we're going to have to traverse this, we're going to have to start at head, and then we're going to say, if this is a linked list, we would say print. This is very similar at it as a set of nested dictionaries. And that is linked lists under the hood. Okay, so now we're going to look at linked lists under the hood. So we're going to start with so now let's create our constructor for our linked list. And we're going to start it out like this. With classes, we're going to capitalize the name of the class. So that names the class, and then we'll build out the constructor. like this. And we saw this in the class video that we start with a double underscore, then a init to initialize this, and another double underscore, and that there's always going to be self as one of the parameters, and this is how you tell that this is a method inside of a class instead of a function. And then we're also, in this case, going to have value as a parameter, and we're going to use that to create the first node at the time that we initialize the linked list. But before we get into building out this constructor, I'm going to bring in just the first line of 3 other methods that the constructor has a couple of things in common with, and you'll see why I'm doing this in a second. They are append, prepend, and insert. So the first thing these all have in common is that we pass a value to all of these. And to show you the other, it is going to create a node. It's also going to initialize, it's going to create a node and add that node to the beginning. These it will call on is a constructor. Can assign it to a specific value and self.next and next. And when you have variables that apply to a specific instance, remember we use the self keyword, self.value and self.next. So the constructor for the node is going to look like this. So when we call on the node class, we're going to pass it a value. That is what this is here. And then it gets passed to the specific instance of node. Now that we have a way of creating nodes, we can build out our linked list constructor. So let's bring this back. And our constructor is going to start off like this. So we're going to pass it a value so we can create the first node in the linked list at the time that we create the linked list. So we're going to have a variable new node, and that's going to be equal to node with a capital N. That means it's going to call the node class, and we're going to pass this value here to the node class, and that creates the node. Then we say self.head equals new node. So we'll bring the head in here, and that points to the new node. Also self.tail equals new node. Now we have tail also pointing to the new node. And then we're going to keep track of the length So we're going to start the length out by being equal to 1. And that is our linked list constructor. Now that we have this, we can create a new linked list. And we could do it like this. My linked list equals linked list. Notice this has the capital L. It is calling the linked list class, and we are passing it the number 4. And by writing this line here, the my linked list, you are creating all of this. You have created a head and a tail 4. So let's go over to the creates. That's going to be the value of that linked list. Construct to create that first node. We created the node, we can come down value. That value of 4. All right, so it looks like we have a working linked list constructor. And that get constructor. So now that we're getting into writing the code for our first data structure, I want to remind you of the 2 different ways you can access the coding exercises in this course. So I'm going to flip over to the course, and then if you come up here to the constructor video, the one we just watched, and you click on the resources tab, underneath that tab there is an exercise file. If you click on this, that is the exercise that goes with that video. And you can access the same exercise file by scrolling to the bottom down here and clicking on coding exercises, and all the same coding exercises are down here. So I'm going to click on this one for the constructor. It's the same one we just downloaded. That will load this. And I've marked out exactly where you're supposed to write the code. You can see here it says write node constructor here and linked list constructor here. And I already have the correct code copied. I'm just going to paste it here. And then you come down here where it says check solution, and it says well done, your solution is correct. So you can write all of this code down here as well. And if you do get stuck, I do have the solution over here. And that's the same code that I just copied in. So I'm going to encourage you to take a moment and do this coding exercise for the constructor. And then if you look over here, you can see that there are dozens and dozens of these coding exercises. So now that we're getting into writing the So in order to look at all of the values in a linked list, I've created a method called print list. So I'll just walk through this quickly. It's pretty simple. It's called print list. Then we have the variable temp equal to self.head like this. And then we just have a while loop that goes through the list. And while temp is not none, in other words, we haven't reached the end of the list, we're going to print temp.value, in this case that's 11, and then we say temp equals temp.next. And that just moves that over, and we'll print the 3 and the 23 and the 7. Then we reach the end where temp is equal to none, and then we stop running the loop. So this is pretty simple. We'll be using this as we go through the linked list methods. That we're going to create. I just want to point out that this is not a built-in method. I am creating this. And I've also created similar methods to print out the contents of all of the other data structures that we're going to create in the course. I won't walk through that when we get to the other data structures, but understand when we do print graph, that is something that has been created. All right, that is print list. So now we're going to write the method to append an item to the end of the linked list. So that's going to look like this. We're going to create a new node. We'll have that last item that was in the list point to the new node. will have tail point to the new node, and that adds it into the list. So there were two things we did here, last item and tail pointing to the new node. But we do have an edge case for when we don't have any items in the linked list. Obviously, we can't have the last item and tail point to the new node because there is no last item. In this situation, we're going to have head and tail point to the new node. So if you want to code this, these are the steps for doing the append method. Pause the video here, go over to VS Code and see how far you can get with this, or if you can write the entire method, and then come back and we'll walk through it. So now we're going to get into the code. So of course, with the append, we're going to pass it a value in order to create that new node. And it has that self keyword in the parameters. That's how you know it's a method inside of a class versus it being a standalone function. So we'll say new node equals node. We'll pass it the value that we pass the append method, and then the node class will create our node. I always like to code for the situation where these data structures are empty like this first, where head and tail is going to point to the new node in this case. So in order to do this, we have to determine, is the list empty? So I'm going to say if head is none, which is the case here, we'll set head equal to new node like this, and then we'll set tail also equal to the new node, and now head and tail point to the new node. So let's take this code and add it in with the rest of our code like this. This is what we have so far. So now let's code for the situation where there are items already existing in the linked list. We'll say else, and now let's build out this else statement. So we're going to say tail.next equals new node. Okay, and that is tail.next. We're setting it equal to the new node like that. And then we're going to move tail over by saying tail equals new node. That moves that over and adds that node into the list. Now let's add this else code back in with the rest of our code like this. Okay, so let's look at what we've done here. We've created a node. We've tested to see, is this list empty? In this case, we're going to do this. Otherwise, we're going to do these steps here. The only thing left to do is to increase the length of the linked list by 1. And there's one other thing I'm going to do here, and this is completely optional. I'm going to have it return true. And as a standalone method, this is actually not necessary for the append method. But the reason I have it in here is in a few videos, we're going to write another method that calls on the append method. And that method requires a true or false to be returned. So we're going to look at this code in a moment in VS Code. And when we do, we're going to create a linked list that looks node with the value of 1 with the value of 2. And then we'll print out the linked 2 in our linked list. Linked list class linked list. Say my linked the number dot print list. You should see 1 and 2 printed out. So it looks like we have a working method for append. Okay, so now let's do get. So now let's look at popping an item off of the end of the linked list. And we're going to split this up into 2 videos because this is a much more complicated operation than pushing something on. And we touched on this in the linked list Big O video about how pop is a more complicated method. So I'm going to bring up our linked list like this. Pop is going to look like this. We're going to remove that last item and we're going to return it. We have 2 edge cases. The first edge case is if we have an empty linked list. And then the other edge case is if we only have 1 node in the list. So if you want to have a challenge, pause the video here and try to code this without watching the rest of the video and then come back. Otherwise, I'm going to get in deeper to the logic of how we write this, but we're still not going to get into the code in this video. We won't do that until the next video. The thing that makes this more complicated is when you move tail to the left like this and remove that last node, tail is moving the opposite direction of the arrows in the linked list. The arrows are all pointing to the right and tail is moving to the left. So let's put this back and look at this from this kind of a perspective to better understand what we're going to have to do here. So what we want to do is move tail to here, set tail.next. next to none, and then return the node that we've popped from the end of the list. So let's put this back the way it was and look at what we need to do that. We need tail to point to this node. In order to make tail point there, we need to set it equal to something that is pointing at that node. And the only thing that is pointing at that node is the next value in this node. So that means we have to get to this node. Well, the only thing that's pointing at that node is the next value in this node. And so on until you get to the head. So that's why you have to start at the head and move node by node through this list until you get to here. And then you set the tail pointer equal to that pointer, and that's how you get tail to point at that node. And then you say tail.next equals none. Then you return the node that you popped from the end of the list. Okay, so let's put this all back like this. So if you weren't able to code it before, if it was too complicated, this is another place that you might want to pause the video and take a crack at it, because I'm going to get into a little bit more detail of how to approach this. So I'm going to bring in two variables, pre and temp, and I'm going to set them equal to head. And for now, I'm going to just remove head and tail, and I'm going to move pre underneath like this. So what we're going to do is we're going to say if temp dot next is not none. In other words, we're not to the end of the list. What we're going to do is we're going to set pre equal to temp, which it is already in the first iteration, and then we're going to set temp equal to temp dot next. And then we're going to do it again, is that none. We're going to move pre up and temp over. And we just keep doing this, and this will be the last time that it's not none. We're going to move pre up, temp over, and now temp.next is equal to none, and these stop right here. So we're going to need that temp variable to return that node that we're popping off the end. But for right now, I'm going to remove temp, and we'll work with the pre variable first. The only thing the pre variable is for is we're going to set tail equal to pre. And that's the only thing we're going to use it for. That's going to move tail back. Then we'll say tail.next is none. That breaks this off the end of the list. And remember, temp is still pointing here. We need that to be able to return this. We'll say return temp, and that returns this node. So we will code this in the next video, but for now, that is our intro for pop. Now let's code the pop method. So we'll start by just saying pop. We don't pass us any arguments. And remember, we had 3 different scenarios to code for. I tend to start with the one where we don't have any items. And there are a few ways to test for this. You could say if head is none, tail is none. I'm going to, in this one, say if the length is 0, then we'll return none. So the next situation we're going to code for is if we have 2 or more items in the linked list. And as we discussed in the last video, we're going to have 2 variables that are going to be temp and pre. Let's create those. We'll say temp equals self.head and pre equals self.head. And then we'll walk through this with a while loop. And we're saying while temp dot next. In other words, while temp.next is true, if it's pointing to a node, it's true. And where this is going to become not true is at the end of the list where that pointer is going to be none. So there are a couple of different ways you could write this. You could just say while temp.next, like I did here, or you can say while temp.next is not none. So this is a little bit more concise. You might argue that the other way is more descriptive and more readable. I will do it both ways in this course, but for this one I'll just say while temp.next. And then inside the while loop we'll say pre equals temp, And in the first iteration, pre is already equal to temp. And to move that temp pointer over, we're going to say temp equals temp.next. Okay, so let's walk through this step by step. We'll say while temp.next, and in this case, temp.next is pointing at a node, which is going to make this true. We'll say pre equals temp. In the first iteration, it is already pointing to the same node as temp. Then we'll say temp equals temp.next, which moves temp over like that. So let's walk through this all the way to the end. We'll say while temp.next, we move pre up and temp over. This is true again. We'll move pre up, temp over. And then this will be the last time this is true. We move pre up, temp over. Now we say while temp.next, this is going to be false. So we stop running the while loop right here. So for now, I'm going to remove that temp variable. It's pointing at that last node. We will need that in a minute, so I will be bringing that back. But for now, I'm going to remove that. And then we need to have tail point to that 7 node. We do that like this. Self.tail equals pre. And that's going to point that there. So that's the only thing we're going to use pre for. So I'm going to remove that. Then we need to take that 4 and break it off from the end of the linked list. So we'll do it like this. Self.tail.next. That is tail.next equals none. Okay, so that's our code for when we have 2 or more items in the list. We had also created these 2 variables. And let's add this in with the rest of our code. This is what we have so far. And then we're going to decrement the length by 1. But it still leaves us with one other edge case. That's the situation where you have 1 node. So let's walk through this situation. We have head and tail pointing to it. We have temp and pre set equal to head. So that's going to look like that. All 4 of these pointers are going to be pointing at this 1 node. So the 2 highlighted lines of code there, temp and pre, I'm going to remove those 2 and everything above it, and we'll walk through these now. So we say while temp.next, so temp.next, in other words, while temp.next is not none, we're going to run this loop. Well, right off the bat, this equates to false, and the while loop does not run. So let's remove that. And that's all we're going to use temp for, so I'm going to drop that out. Then the next line is tail equals pre. Well, they're already pointing at the same item, so that doesn't do anything. So let's remove this line of code. Then we'll say tail.next equals none. Well, tail.next is already none. That doesn't do anything. Then the only thing left to do is to decrement the length by 1. So the length was 1, because we had the 1 node in there, and we decrement it to 0. So we ran through all of these lines of code. We decremented the length to 0, but the problem is head and tail are still pointing at that node. So we have to correct that. So let's bring the code back here, and then we'll have to add a few lines of code. We'll say if the length is 0. So we have another if the length is 0 up here. But the one down here is after we have decremented it. So we had started with 1, we decremented it by 1 with 1 item to return temp, which returns the node that we just removed. Okay, so there is all of our code for pop. So we'll look at this code in a moment in VS Code. And what we'll do is we'll start out with 2 items like this. Remember, we had 3 scenarios here that we had to write code for. 1 if we had 2 or more items. So we'll run pop to see if that works. Then we're going to be left with one item, and we'll run it again to see if it works with one item, and then we'll see if it also works when we don't have any items. So let's flip over to VS Code. Okay, so there is our pop method, and this is where we create that linked list that we just saw with a 1 and a 2 node in it. And I'm just going to print the list so we can see that we have a list with 2 items in it. So we'll run this. And that is our 1 and our 2. All right, so I'm going to scenarios here. We're just running pop, returned 2 nodes, and then it returned none. Test it. You want it to return. So that means we have a working method for pop.
I don't have time for testing. We've all thought it, we've probably all said it, and we certainly know of organisations that think it. In this video, I want to look at what makes testing bad for productivity and what we can do about it. Before I've even had a chance to get of us being productive as now, this existing code might be something that we wrote a week ago. Or it might be something that someone else wrote 3 years ago. Certainly the latter case is more challenging, but even the former case where we wrote it a week ago, there's a good chance we've forgotten what we did and why we did it. Writing tests for existing code is challenging. We don't always know or remember what the code is, particularly test. Dave and I would probably argue that the thing you need to do is be close enough after writing the production code that we can remember what it does, and that and we're about to sit down and write the test for our code. It's hard. It requires to think about it when we're malformed input in, then the code should. Or even local tests which just happen to have a lot of dependencies and have a lot going on. A test that takes a long time to run is not a development flow all the time. Testing pyramid as possible. We can also use techniques like running tests in parallel where hours, maybe even first-class citizens. Assumption. No, thinking is the thing that we get paid for anyway.
When you start seeing things in terms of patterns rather than technical details, you've opened your third eye. You will reach a new level of consciousness or dynamic. And the reason is that when you really understand what these things mean, learning a new programming language is pretty trivial. Have one variable set to a number, have another A and B. You shouldn't really try adding a number with a string, but if you don't know the type, God forbid you try to even get a runtime error occur at runtime. Details, you kind of see things looking at, you have a client, the client and the server. The service, Stripe, is going to respond at some point, either it's success, okay, the status of the event. Eventually respond here, called a retry. This is our similar subscriber pattern in distributed systems, where we don't want a fundamental concept. Now with PubSub, or you can do HTTP polling. See it from a higher level, and then you'll see every time you learn a new concept, and you searches, but this concept, it's in the name. It's not statically typed, and buffs as well. What about you define the type before you client-side applications, you might code actually when you start, but they boil down to the same patterns. That's why patterns are so important with LeetCode, with distributed systems, with programming languages, literally everything. Unfortunately, so our friend John
on Hacker News and read an
write vanilla JavaScript. Oh wait, so our friend Jonathan Blow is back, and he's going to blow us all away again with his hot take. Current software engineers have no deep knowledge.
I think there's a pretty serious problem that started happening in programming culture. I mean, it's been in programming for as long as I've been in, and this is beyond games even.
You know, in the old days, they had like they had those. I don't know what I'm doing, and that gets like 1 million views, and everyone likes it, which I think. Idea what they're doing. You read a tutorial. Springboard. Like becoming a good pro. I think it's more an industry failing. Again, with to fix that, and so it's been this kind of mantra. But I don't know if it's actually fixable because you still have to convince everybody else that once you hit this plateau of like it's starting to get better, that you can't. If you want to ignore that, what I would say is. All your other metrics are downstream of performance. And the reason for this is because code is very fast when it doesn't have much code. That's how it works. If there's very little code happening, then it is very fast. Yep. So the old classic performance mantra. If you could just not.
Programming principles, they don't teach them. How easy would it be to debug the code if over 80%? So you have to go through all these to hard code like 3 times. It makes sense to put it in a helper function. If it was just 2 times though, at that point I think it's debatable. There's nothing wrong with putting it in a function at that point, but I don't think it really matters that much, because at least in my experience, perform only one of t, then any properties provable by t must also be provable by s. So that's, I guess, the math definition, but it's pretty simple. If you have a penguin class here, which inherits from the bird class, and the bird class has these methods, fly and eat, you should be able to call those methods on the bird as well. Technically, this has the fly method, but it does throw an exception because a penguin cannot fly. So it technically does break the substitution principle, because I was not very good at LeetCode when I first started. You guys want to see my submission history? I want it to be known I was not 3, 12, 13, 14, and maybe I just gave up and copy and pasted somebody's solution. So I was not very good at all when I first started. So 2 p.m. I started, and that day, my last submission was at 3:40. I sat at this one problem for over an hour and a half. At least I understood it by the end of that, hopefully. That was day 1 of LeetCoding for me. I wonder what other problems because I one-tapped this one. Where was the daily challenge yesterday? I don't know if I should make a community post. Time on LeetCode varies a lot, so if you ever see multiple submissions on the left, sometimes I just submit it multiple times to get a good runtime, so then I can say, and it's pretty efficient, cut the video, and I'm done. That's it. Doesn't take me very long to make. In the real world, dumb people need safety guards so that they don't make dumb decisions. You don't want someone to take on a car loan that they can inferred as the any type. But the problem to code this thing, no explicit any. The code being dynamically typed, you're going to end up with events and other objects that are casted as any. And the time it takes you to figure out what the type is actually ends up slowing you down. To paraphrase this fantastic video I watched on the topic, TypeScript is only successful as the ecosystem that supports it. Given that types are optional, there's
So when would you want to use an interface? Let's take the simple example. Of you going to eat at a restaurant. So here you are, you're getting ready to go eat at the restaurant, and the waiter brings you out a menu. Now the menu I want you to think of as an interface. And what is an interface? Well, an interface is a contract saying what are the things that we can do for you. So here at the restaurant, this is an Italian restaurant, they say, well, here we can make you spaghetti and meatballs, we can make you baked ziti, spaghetti and meatballs. Is the interface between you and the restaurant. So the restaurant says this is what we provide. This is our contract of goods that we can do for you to the kitchen. And so your spaghetti and meatballs. Now this is the contract between restaurant. You go over here and say, hey, folks, we need some spaghetti and meatballs. And so now over at this things we can do. And then the implementations are these restaurants. These are who implemented the interface. This restaurant A implemented the interface and restaurant B implemented the same interface. They both said, hey, we can both make you spaghetti and meatballs. Now, how they do that, you really don't care about. The caller of that, from the interface perspective, doesn't care about it. The caller says, hey, I want spaghetti and meatballs. At the end of the day, you know that you've just been delivered the spaghetti and meatballs that you want. You don't care how it's done. Now, behind the scenes, the implementation could be different. For example, if this is code, this code might call into a completely different module to from a keep going, and there could be. So it doesn't matter if you're ordering spaghetti and meatballs from this location or any of these locations. They all know how to return back to you the spaghetti and meatballs that you want, all done through this interface. Now, if you take this a step further, and we can go ahead and kind of clear this thing out. Again, you have or whatever. This is just an interface too. Think about like a graphical interface. This is an interface that's been one will be up here behind interface. If I tell the mammal to walk, it will walk. So anytime you want something to adhere to the same contract, you can do that. And that's exactly what has happened over inside of the examples here. In this case, we're using mammals. So we can have a mammal, and it can have be a cow, it can be a human, or whatever. We know that it walks, it can speak, whatever. But all we know, 15, I don't know, don't care. I just know that it walks. To implement an interface, and then the name of the interface, as in something might be able to be discounted, such as a physical product. And inside of there, I would want the implementer to implement. So here I'm going to implement a function called discount %. The discounted items. Create an interface that is called, doesn't have a return type. It doesn't have to be. It might be something such as of your function. to implement an interface in Kotlin, you'll want to actually create a class. So you can say class, and to extend and implement the which ones. We can select discount %, and then what we have to do is we have to implement whatever that value is. And of course, if we do not implement it, we can leave the default to do here, which will then, if we look at the implementation, we'll go ahead and throw a not implemented exception log saying that this has not been implemented for later. We're on here, so let's just call this foo for whatever reason. Anyone else who has implemented discountable. So and you will also need to implement both of these values on. And some examples of this might be you build an interface for your file system. So if you build a file system interface, implement these members, empty string. Of course, we would. Now this is great because we have the ext file system, we have the FAT32 file system, and we know that anytime we're working with a file system, we need to do something. Now, file system to file strings. That's all I know how to do. I don't care how it's done. When creating interfaces, it's very often that you'll do it in an anonymous fashion. Here, I have set up an interface called onClickListener. This is something you've probably seen in various other UI toolkits. And this onClickListener has an onClick method that is called when a particular view is clicked. And so we have a class here called view. This could be such as like a button, a text view, an image view, some type of clicked. It'll then instantiate the click listener, and then whatever happens inside the click listener will happen. So that's the interface here. onClickListener with a onClick method. So we have a few other classes that extend view, such as button, image, and map. So let's assume we create a button here. If I wanted to set the click listener, and perhaps I want to say print line. Now this is not an anonymous implementation. This is a concrete implementation. So let's go ahead and get rid of this. This is not what we want here. There's a way we can do it directly in line here. And so what we're going to do is we use this word called object. We're basically creating an object right here in place. And we'll say click listener, and then open and close brackets, and then you'll see object is highlighted, and you hit Alt Enter for Mac, and implement the members, and it'll just allow you to implement that member, which is on click, and then we can just do print line here and say this was clicked. And of course now if we run this, and it was called here and directly set up accordingly. So that's how you can create a new instance of that. Now, sometimes you'll also see methods perhaps that allow you to, inside of here, we could say button.set. This was clicked, and just to show some differences here, say this was clicked ABC.
Interfaces are a way to describe this. Do things like that will return, and then we can. So now we're using. Enjoying it. Make sure to hit that like button, and if you're new here, say it's a 42. We need a name. Call signable to type number, so we can set this to 52, and everything is happy. We can also do other things. So let's say we have membership, and we all know our membership is only going to be 2 properties. It's either going to be basic or super. So we can actually denote that membership is going to either be basic, and then using a pipe, we can say basic or super. Those are the only 2 options. Now, if we add this to our user props here in our user function, and we say membership, and then we open the string, you'll see that the only values that are available are the ones that we want. So let's make it super. And then, so we could say credit card, null. And this person doesn't have a credit card, but we could create user.